Good afternoon. Thanks for coming to my talk. I'll be talking about, as you can see, DataFrames and their scaling. But before we get into that, I want to take a moment and describe what has happened in the past few years in the Python community, because I don't know if you've seen this blog post from Stack Overflow from last year, from September, where they basically mapped what happened on the Stack Overflow side over the past 6 or 7 years to help understand why Python has emerged as such a popular language for the data science community and beyond it. And they noticed that one of the main reasons was the pandas package that most of us, if not all of us, use on a daily basis. And they found it was the fastest growing Python-related tag on the site. And here you can see it as a chart. So you can see projects like Django and Flask, which are growing more modestly. And then you've got the sort of scientific computing stack of pandas, NumPy, Matplotlib. Scikit-learn is not here, but I'm sure that the growth will be similar. And before we go any further, I wanted to focus on sorry for the pun, on NumFocus and PyData. So NumFocus, if you don't know, is an American nonprofit that focuses on fostering communities and sort of helping the open source scientific computing stacks. So, and you may know them by their most popular educational track, which is called PyData, which organizes now it's over 100 meetups around the world and almost a dozen conferences around the world. And I was at a PyData conference just last week, and I realized earlier than that we don't have a PyData community within the Czech Republic. Whilst we have a lot of users of the PyData stack, we don't have a coherent community. As you can see on this map, even in Europe, there's a number of spots, including Slovakia as of last year or 2 years ago, a number of them in Poland, a number of them in Germany, but none in the Czech Republic. So I wanted to take this opportunity, since there's quite a few people here, and some others might see it online. If there are any volunteers, anyone's interested in fostering the community and helping out popularizing the open source approach to scientific computing, then please get in touch and we could do something together, and maybe we'll get a PyData meetup in the coming months, or maybe even a conference in the coming years. So this is just a very quick plug about the open source community and NumFocus. So before we get to the scaling, let's talk about DataFrames in general. So what are DataFrames and why do we like them? So you probably know what DataFrames are. I just wanted to emphasize some of the key characteristics. And this is sort of more or less comparison to the more traditional SQL-like data stores. So how are DataFrames different? So they're in-memory data structures, or the typical implementation is an in-memory data structure. The schema is very flexible, so sometimes we struggle, doing like pivots and unpivots in SQL. This is something that's very, very simple and very easy to do in DataFrames. There's also a very good domain-specific language, so you've got all the sort of group bys, value counts, and that sort of stuff, which really helps you to chain all the commands together and everything. And one very powerful thing is user-defined functions. So this is something that is usually quite problematic in SQL databases, where you usually have a limited language to work with when you want to use some custom code. Whereas in Python DataFrames, you have all the power of Python itself to manipulate your data. So that's very handy. Also, there's nothing to worry about in terms of runtimes. So you don't have to be careful about you don't have to worry about servers sharding and that whole thing, because it's all running within the process that your analysis is in. Also, there's a few performance benefits like columnar processing. That's something I'm going to be talking about in a bit. There's no specific data store, like with some databases you get specific data stores, but with DataFrames it basically loads everything into memory, so it's fairly agnostic as to what the source of the data is. And you also can obviously combine multiple data sources, which is also possible in other systems, but it's very rich in pandas DataFrames. So this is just a very quick summary of what DataFrames are, why we like them, and why we don't want to let them go if we scale up and out, which is the point of this talk. So the main problem that I want to solve is that a lot of people just start with pandas is by using read CSV. So you have some data in a table in a CSV, you read it into memory, you work with it, you export some results, and you're good to go. But over time, that data might grow beyond what your machine is capable of processing, and you want to you're sort of wondering what next. What tools can I use in order to handle this growth, and do I have to leave the DataFrames API in order to do that? And over the years, we've done this a number of times at various companies, and we devised a number of solutions that would overcome this problem. And I want to emphasize up front that there really isn't one size fits all solution. Every one of these solutions has its downsides and usually quite a few upsides. So it's always about choosing the best tool for the job. So I wanted to say this up front. So the 4 solutions I have here, well, only 3 of them are actually scaling. So the first one is actually don't scale, just write better code, essentially. The second one is scaling up, also known as vertical scaling. Third one is a bit of a weird one. I'm going to get to that. And the fourth one is scaling out, so horizontal scaling, adding more nodes to your system. So when you're on your single machine on your laptop doing your analysis, there might be a few possible bottlenecks. You've got your CPU, you've got your memory, you've got your disk, and the main 2 that I wanted to focus on is the CPU and the memory. So Pandas itself is very fast in terms of aggregations and analytical functions in general, but it's sometimes us that we actually slow it down. So I've seen this a number of times, that people actually loop values within a pandas column, try to apply some code to that value, and then save it back to that column. So you've got a lot of locks and adds and trying to address specific fields within your data frame, and that can get very slow. And the one thing to realize is that every column is every column is stored in a contiguous manner, which is very easy, which is very handy for a vectorized operation. So if you operate on columns as objects as a whole, then your code is going to be much faster because you're not going to have all the overhead of looking up values and saving them back in. So instead of looping, just consider using the columns as a whole. This is just a simple example where you're taking the column X and just applying a function across the whole thing, and squaring another column and just saving it as a sum in a whole other column. And this can be, we've seen something around 100x, 200x performance improvement by doing so. And also your code gets a lot cleaner as well. So, and also if you write your own code, just consider computer science principles, like the big O notation stuff. So hopefully I don't have to go over that at this point. But yeah, just don't use slow code when working with pandas. That's what I'm saying. In terms of memory, which is another thing, so if you're using, if CPU is the bottleneck, then your code is just going to run for a long time. Sometimes it doesn't matter. You can just let it run in the background and get back in 2-3 hours, and it's going to be done. Sometimes when you have memory pressure, you can't do that. Your code simply won't run. You're going to get a memory error, and there's nothing you can do about that. There's a few things that you can do to fix that. So there's 3 questions that you can ask. So do you actually need all the data in memory? Oftentimes you just want to filter out some rows and just save them someplace else, so you can iterate by chunks. Sometimes you don't actually need all your data, period. This doesn't apply if you want to do something like a sum per every customer, so you actually need all the data for this. But if you're sort of looking for characteristics of your customers, you can only take you can take just a sample and leverage things like the properties of large samples. And last thing that you can ask yourself, do you actually need all the columns? Because you can have a data set with 100 columns, but your analysis is only done on 3 or 4 of them, and you can actually specify which columns you want when you're reading in your data, and right off the bat you can get 3x, 4x, 5x, 10x memory improvements just by selecting specific columns. Last but not least, you have to consider the data types, the types that you store the data in, because if you use, for example, numerical data, you always want to use the floats and ints, because these are saved in NumPy arrays within pandas. which is very memory efficient and also very performant. If you've got strings and you've got a column, say a country, which can only have so many values, you might want to consider categorical values, because this is essentially saying I have this limited set of values, let's say 200, and it's going to map each value to a number, and it's only going to save the numbers within the column. So again, instead of having a million pointers and a million strings somewhere else, you're going to have a million numbers and 200 strings, which is a lot more memory efficient. And you can do all of this within read CSV and other methods. So use calls, you can select only the data that you want to read in. Chunk size, if you want to iterate over chunks of your data one at a time while still using the DataFrame API, you can specify that. You can parse dates, so you don't have dates as strings, but as actual date objects. And you can also specify dtype category to parse into categories. And you can also do this post hoc. Once your data is loaded in, you can then work with dates and change types, etc. And a bit of a heresy, do you actually need pandas to do your work? The reason I wanted to mention this is pandas is fast, but it's only fast once the data's actually loaded in. If you don't have the data loaded in, then you can't really do any analysis. So if the process of importing the data into memory is actually very slow and feasible, you might want to consider streaming through your data and doing some processing on the fly. And you might be wondering, oh, can I do my group bys and other things that require multiple rows or multiple rows in memory? And yes, you can. You can do group bys and all that stuff while streaming your data. So this is something you might want to consider, because then you can use your run-of-the-mill laptop to process tens of gigabytes of data, which is something you can't do if you load it all into memory, which is going to fail fairly quickly. And last but not least, take a look at the documentation for collections and iter tools, which are two of my favorite packages within the Python standard library, which basically implement a lot of the aggregations and iterations functions that you will ever need for your analysis. So 12 minutes in, we haven't scaled up or out yet. So let's get to that. So scaling up is basically just getting a beefier machine to do to handle your analysis. The great thing about this is that you're not actually changing your code. You're just using your code on a beefier machine that has more RAM or more CPUs or both to speed up your analysis or to actually handle your analysis. And there's at least two ways of going about this. You can do this locally, and while that might sound a bit amusing in the age of cloud, if this is your day-to-day work and you don't have a laptop but you only have a workstation and you're going to be doing this analysis 8 hours a day, it might be cost-effective just to get a more powerful machine at work. This is something we did at work years ago, and it paid off tremendously, because you spend a couple €100 to get 30 gigs of RAM, a faster SSD, and off you go. It might sound obvious, but it's something that's not obvious to everyone, I suppose. The more fun part of scaling up is when you use remote machines. So this is basically getting a virtual private servers. This is a very elastic way of getting more compute for your analysis. And just a few years ago, this was quite difficult to set up. You did have to have a DevOps team or someone to help you out with this. So you can just say, oh, I want a machine with 64 gigs of RAM, or even more than that. You would have to be either waiting hours, or you have to have some external help. As of just a few years ago, the UX, the way you provision these has improved tremendously, and you get other benefits because these machines are usually in a data center which is connected to great internet. So if you're doing analysis of, for example, Wikipedia dumps or something like that, you can get the data in to your machine a lot quicker than you could to your laptop. You also get billing per hour, or if you're in AWS or Google Cloud, you can get billing per second. So that can be very cost effective. But as I said, if this is something that you're doing day to day, it might stop being cost effective. So there was a discussion on Twitter just a few weeks ago where somebody noted, oh, you can actually get a machine with 1 terabyte of RAM on AWS for just a few dollars an hour. Your data fits into memory, we're done. You can actually get even more than that. I think you can get up to 4 terabytes of RAM on a machine. But then the counterpoint is, what if it gets beyond the terabyte of RAM? What do you do then? And that's something that we're going to be talking about later on. So this is what it looks like. And actually, this is what it looks like. This is a screenshot for like 2 or 3 weeks ago to get an instance on AWS. So this is just, you have to, sort of know what networks and subnets are, what IAM roles are, because if you don't, then you're not going to be able to connect to your machine, because that's actually what I did. So I set up a machine, and I didn't have any ports open, and as I said, I'm not a DevOps engineer, and this is what a company called DigitalOcean introduced just a few years ago. Just compare, 7 steps or 6 steps plus a review to get a machine up and running. And this is, there's a few other bits above and below this, but this is essentially what you're getting. You just select a machine, you select how much memory you want, how many CPUs. You get a straightforward number for your price, because on EC2 you're paying separate for your storage, for the compute and for the network, etc. Here's just $20 a month or $10 a month, and you're good to go. Amazon realized that this is a problem, that there is a lot of demand for this compute for analysts who are not DevOps engineers, and they started offering this. So this is AWS LightSail, which is very similar to what DigitalOcean offers. So you've deployed a server, so you can do your analysis on a remote server for next to nothing, for a few dollars a month. There's a few things to note. I don't really want to go through all of these, but this is just some common practice in terms of security and usability. So adding your own user, using certificates for SSHing, and that sort of stuff. And you may have noticed a few versions ago. So who uses Jupyter? Hands up. Cool. Yeah. So you may have noticed a few versions. So up until a few versions ago, if you launched a Jupyter, it didn't really want any authentication. You just type in the local host and the port, and you're in. If you do something like that on a remote server, somebody knows your IP or somebody guesses your IP, they're in your Jupyter. That's not something that you want. So a few versions ago, they introduced the tokens, that you have to actually enter a token just so that Jupyter knows that you're the one who launched the service. The downside there is that it's still over HTTP, so it's sort of unsecured transfer. So if there's any sensitive data that you're analyzing on the VPS, then sensitive data is traveling back and forth. So you could set up HTTPS or some other security on your remote server. My favorite way of securing my Jupyter notebooks is actually tunneling via SSH. So the fun bit about that is that you SSH so you log into your remote machine, and you say, I want a specific port on my remote machine to act as a local port on my machine. So you SSH into your machine, you do a bit of setup, and then you go to your browser on your laptop, you type in localhost :8888 or something that you set up, and you're in your remote machine, connected securely via SSH, and it's all encrypted and good. So this is a really quick way. So if you sort of know what you're doing, if you do it once or twice, then it could take you maybe 5 or 10 minutes to provision a machine that has, let's say, 128 gigabytes of RAM, and you can just download the data onto that machine and start your analysis, or just port your analysis over from your laptop within 10 or 15 minutes end to end. So this is something that the cloud has really been good for, and as I said, the user interfaces that you use to provision these have improved markedly over the past few years. Last thing about data, since you're probably going to be processing some data, it's quite good to store them in some sort of a shared storage, so you can access it, so you don't have to copy it over SCP or some other way to your machine. One very common good solution is object storage. So this is something like S3 or Google Cloud Storage, or Azure has something like that as well. The great thing about that is it costs next to nothing. I think it costs about $20 per month per terabyte. So you can store 100 gigabytes of data, pay $2 a month, and you also you usually get free or close to free network traffic between the object storage and your machine. So as long as you provision the machine in the same region, you can transfer the data back and forth. So you can download 100 gigabytes of data, do some analysis, save the results back onto S3 or GCS, and it's very cheap. The only thing to worry about is egress, so transferring the data out of the ecosystem out of the network of your provider, but I won't go too deep into that. So third solution, scaling your data source. So this is a great way of offloading the computational power that you need to process your data. So instead of actually getting more machines or a larger machine to load the data, to process it, to aggregate it, you can actually just get a very good database that does this for you. This is a bit of ironic because we're sort of, in the beginning I said, oh, I don't want to use a SQL database because I want to use these nice DataFrame APIs. So in this case, you're sort of have to changing your pipelines a little bit because you have to do a bit of SQL in the beginning and then use pandas read SQL query, which where you supply two things. You supply a SQL query and you supply your connection to your database, and as a result, you get a data frame from your database. So you get all the data types right because usually these are schema on write databases. You sort of sacrifice the UDF support because you can't just apply your Python code usually on the database, but it's something that allows you to scale very quickly and straight from your laptop. So how does this work in practice? So if you have a database that has, let's say, a terabyte of data, you can't just say select star and get it in a data frame because you'll be getting all of the data across the wire. So you'll be doing either some sampling or some aggregations, or even a sampling of an aggregation if the data's too big. But it's something that's very doable and something that's very, very usable. And we've used it on a number of occasions because sometimes you only want the pandas API for the last mile of your data analysis. You don't care that the pre-aggregation, that the sampling was done somewhere else, and then there was a bit of a SQL query in there. As long as you get the aggregation, that you can then pivot, unpivot, and do all sorts of things in your pandas data frame. There's quite a few implementations that you can leverage. So these are basically different types of databases that can handle large scale without a lot of work. So Redshift and Snowflake are basically hosted data warehouses that you pay per hour. BigQuery and Athena are very interesting because with BigQuery and Athena, you just load in a bunch of data and you don't pay per hour. You only pay for the data that you scan. So you can load in a terabyte of data, scan one column, which is say 20 gigabytes, and you're paying for those 20 gigabytes, and you're paying $5 per terabyte scanned. So for casual analysts who only need to run a few queries per month, this is something that's very cost effective. And the last row, Hive, Presto, and Drill are just open source implementations if you want to self-host this thing and you don't want some implementation for, what's the time? There's still 10 minutes left, isn't it? There's still 10 minutes left, isn't it?
Well, in 10 minutes there's another 2 hours.
Okay, I'll speed it up. So yeah. So it's very scalable, very good, but it's but latency can be somewhat different. With DataFrames, you might be used to tens of milliseconds, hundreds of milliseconds. Here it's going to be 2, 3, 5 seconds, or even more if the data is rather big. And I said that you're going to be writing SQL to get your data. You might actually not have to. There are some libraries that are trying to overcome this. Look up IBIS by Wes McKinney, the author of Pandas, who's trying to create an API which mimics Pandas API and translates into SQL. So you're still writing Pandas API while querying your SQL database. And also it benefits your BI tools like Tableau, et cetera, because once you have a strong machine, a strong database in your in your data ecosystem, it's not just you who leverages that. Some other users within your company or organization can do so as well. Last but not least, distributed systems. So this is the scaling out bit, adding more machines to your system. The reason that they're useful is that you can only scale up so much. So you can, at one point, the one machine is going to get, you really can't scale beyond, 4 terabytes at this point of RAM, etc. Whilst distributed systems scale by just adding more nodes to your system. So it's very flexible, and it works the way that you usually have some sort of a coordinator that distributes the work between the nodes. And it scales very well. It can even scale during queries. So you have a very expensive query, meaning it just takes up a lot of CPU, and it just starts scaling out even more whilst the query is running, just starts provisioning new servers, which is something very handy. But the best thing about these distributed systems that I want to talk about, Dask and Spark, is that they're using the DataFrame API all throughout your analysis. So you don't write any SQL code, you just write DataFrame API end to end. And also, that makes the code portability very good, because you can write code on your laptop and then just basically port it over to a distributed system which has 100 nodes and use pretty much the same code. Oftentimes, we use one-to-one, just identical code. So both of these tools, the Dask and Spark, use this sort of notion of graph of actions that can then scale onto individual machines, and then you get the results get reduced once these jobs are done. It's all quite interesting. If you want to learn about the theory, there's tons of talks on YouTube where you can learn more about this. And the way they handle the data is that you get some shared storage, so this object storage like I talked about before, or if you're in Hadoop ecosystem, the data is in HDFS, or you're just taking some external data from the web. The one thing that's quite particular about these systems is that they are usually lazy. So whilst if you do pandas read CSV, you just read the CSV straight into memory, and then you do the work on it. Whereas these systems work the way that they wait for you to take some action. They wait for you to write the results somewhere or print something, and only then do they start doing the work. So whilst pandas is eager, these are more lazy solutions. Dask that's just a Python system that tries to distribute Python work across a large number of machines. Spark is a Scala system, so that's a JVM-based system, but it has Python processing running alongside it and interchanging data with the Scala processes. And it actually has a very nice Python API, so you actually feel like you're writing just Python code when working with it, so don't be worried that it's JVM, which is, JVM. So how do you actually work with these? So the great thing, as I said, you can start developing on your laptop and then scale out to a number of machines. And as of last year, you can just pip install both of these. I said that it's a JVM system, but if you pip install PySpark, it actually downloads all the jars and other nasty stuff and just works on your laptop. And if you're working on a distributed system, there's a number of hosted solutions by Databricks, the creators, well, a company founded by the creators of Spark, and EMR, Dataproc, and HD Insight are Amazon, Google, and Microsoft solutions for this. So similar to the scaling out of the data source, it's got higher latency because it's got a lot of network connectivity, a lot of network communication. But the great thing is that it's really easy to migrate your code from your laptop to a cluster. So the scaling is a lot better because you're just adding nodes to your system and it scales horizontally from there. The one downside of these systems is that the debugging can be quite hard, especially if some random node just fails, or your code on a random node fails. It's quite difficult to trace it to that node and get the tracebacks and all that. So that's the one downside of these systems. So to close, there really isn't a silver bullet. All of the solutions, some of them have downsides, some have upsides. Think about all the costs, not just the hardware, because we're programs, we're expensive, and be careful about writing complex code just to save a few milliseconds if you can use a more scalable solution to do the same equally quickly. has some further reading that you can then click through, and that's all from me.
Okay, so let's go right to the questions. So, any tips how to debug PySpark code running on cluster?
Don't. Just so it really depends. It really depends. So if you're using the built-in APIs, the error usually bubbles through and just tells you, oh, you forgot that your data is actually integers, not strings, or vice versa. But so you can actually scroll through the 7 kilometers of tracebacks that you get from PySpark. But if you're using something like UDF, so user-defined functions, so your own custom Python code, and that fails for some reason, you're pretty much screwed. And it's quite difficult. And I deal with this on a daily basis. I even tried to, run a debugger within that function, and it just sort of went nowhere because PySpark doesn't really work with the run-of-the-mill debugger. So this is it's an unresolved issue, and I would love it if it was resolved somehow.